these for too long. Let's get started. I want to make one comment about the homework. I've had some people come into class, into my office hours, and Alex has also reported this. A little bit of confusion about this uncertainty notation. So, for instance, in problem 2.2, I report that x is this value. So it's 2 with this uncertainty inside the parentheses. And I just wanted to give you just kind of like a 30-second way to interpret this. And the idea is that the error, this is the error, which I write delta x, little delta x, is in this parentheses, and the error is in the unit of the last unit of the is in the units of the last digit in the number, right? So this is 20 units of 0.01 uncertainty, right? Because the last digit is the hundredths place. Right? This is 21 hundredths of error. So that would make this 2.00 plus or minus 0.2 centimeters. Right? So if I were instead to write, for instance, I would never write this, but if I were to write this, what would the error be?
2 plus or minus 2.
Exactly. 2 plus or minus 2, right? Because there's 200 units of error in the hundredth place, right? So that would be 2. Right? And likewise, if it were this, that would be 2 plus or minus 0.02, right? Because there's 2 units of 1/100th of uncertainty. Okay? And another question is how does this tie into significant digits? And the answer is it doesn't. This is the exact replacement for significant digits. Significant digits are an approximation, right? They're a way, if you aren't given exact uncertainties, how to approximate what the uncertainty is within an order of magnitude or within one digit. And so when you're given an error like this, you don't have to worry about significant digits because you know exactly the uncertainty in your value. And so typically, the like big Illuminati that runs chemistry, the IUPAC, they typically say that you should report 2 units of error. So that's why you typically will see something that looks like this. It's just kind of a standard practice. So if you're not given uncertainties, exact uncertainties, you should think about significant digits. But if you're given uncertainties, then just use the uncertainties. All right, yeah, please come on in. All right, any questions about that? Okay. All right. I'm going to close this. So today is a derivation day. We're not going to do much problem solving today. We're just going to grind out a very interesting result from our box. Right? We're going to start working on our box. And the derivation we're going to do today is the ideal gas law. We're going to derive it from first principles. Right? But we should probably remind ourselves what our assumptions about ideal gases are. Right? And so I'll just rewrite those real quick here. So ideal gas, approximations, or assumptions, however you'd like to think about it. One is, again, each particle or element is point-like with a mass m, which means it has no shape or size. It's just a point with a mass. 2 is that the particles don't interact. It is a free model, if you will. There's no attractions or repulsions. They're just billiard balls. Each particle moves randomly in accordance to Newton's laws of motion. And finally, I'll write it down the bottom. Probably can't see this, but I'll just say it. Each particle has perfectly elastic collisions, right? Which means they just bounce off. They don't exchange energy with each other and the walls. Right? So the particles can hit each other, and they can hit the walls, but they can't exchange any energy. Right? And these are enough assumptions for us to be able to come up with a formula that allows us to describe the state of our box. Okay, so what we're going to do with this is we're going to take these assumptions with the fact that they're random. Remember, at the end of the class, we derived this formula called the Boltzmann distribution. We talked about if you were to pick a particle out or a set of particles out, what's the probability of finding them at a certain energy? And so the idea is that the number of particles in some energy state, right, some number of energy, with energy E sub I, which is any old number, is proportional to e to the minus ei sub I over kt. Right? So it's a fraction. So the energy is an exponent of the ratio of the energy of the state versus the available energy from thermal energy, from heat, if you will. Okay, and this is enough for us to get from here all the way to Pivner. Okay? So that's what we're going to do today. We're going to kind of do it from the simplest, well, not the most simplest way, but rather the most precise way, if you will. All right, so we're going to kind of use some hints here, right? That we should probably look at Newton's laws if we're going to think about the motion of these particles. If they're elastic collisions, that means we can use Newton's third law, right? Every action has a reaction, right? There's no energy loss, no loss of momentum. Everything is conserved, so we can probably apply Newton's third law somewhere. When it means that they move randomly, that means we can use Newton's first law and Newton's second law, right? And so on. So we'll come across those as we move through it. Okay, since the particles are point-like, they don't have any interactions. There's no potential energy. There's no gravity, so let's ignore gravity here too. So that means the only energy of the particles are, so let's say this instead, all the energy of the particles, or the atoms, is kinetic energy. Right? And kinetic energy, which I'll write T, for a given particle is 1/2 times the particle's mass times the velocity squared. Right? And I draw velocity as a vector because it's in 3 directions, and we have a 3-dimensional box. Okay. So that means then, well, look, we know what the energy is of a particle, right? And we can predict how many particles have that kinetic energy by plugging it into here. Right? So we could say the number of particles with a specific velocity squared. Right? Remember, it's squared, so we have to take care of that, would be proportional to e to the minus 1/2 mv squared over kt. Okay, just plug it in. All right, so what did that tell us? Well, it says, well, as temperature goes up, right? So let me think about this. If this fraction gets large, right, then the number gets small, right, because it's e to the minus that fraction. Right, so if this is much larger than 1, then e to that is much smaller than 1. Right, so that means as temperature increases, it means the proportion of finding molecules at a specific velocity increases, at a higher velocity increases. Likewise, as temperature increases, it becomes less likely to find particles at a slower velocity, as we'll see. Right, so there's a balance. Right, so that's maybe not that surprising. All that says is that the hotter it gets, the faster the particles move on average. Okay, so we can always come back to this because we know we can always calculate the proportion of molecules in this at this velocity, and we'll be able to use this expression to derive Pivner once we do a little bit more math. Okay, so what we want to do today is derive an expression which we call an equation of state. For the pressure of the gas in our box. All right, so by the end of this lecture, we should be able to say something like that pressure is a function of some variables, maybe temperature, volume, number of moles, and so on, right? So the number of moles, the pressure, right? We just plug in some things and we get the pressure out, right? This is what's called an equation of state. Right? And we're going to want to derive equations of states for every system we want to look at, because it tells us everything we need to know, right? We've talked about the variables you can measure about your box, right? The box is entirely general, right? It can have a crystalline solid in there, it can have a plasma, it can have liquid, right? Doesn't matter. And the properties of that material are always going to be proportional to some variables, right? And the number of moles, the volume, the temperature, right? The pressure, right? We've looked at all these variables before. All right, so we're going to want to come up with an expression that allows us to express all of these together so we can calculate one given the values of the others. Okay, so that's what we're going to do today. Okay, so we're going to tackle pressure as the most important part. Right? We're going to start with pressure. So we have to start thinking about the pressure in our box. Okay, so we're going to keep it simple. We're going to do it in kind of 2 dimensions. Actually, we're going to do it in 1 dimension, and then we're going to, because it's a 3-dimensional box, we're going to be able to expand it into 3 dimensions later. Okay, so we'll keep it simple at 1 dimension, and then build our box into 3 dimensions, into a cube at a later point. So let's just draw a little part of the box. Let's say, for instance, we take a little part of the box here against the wall. Oh, the marker's dead, so I'm just going to trash it. See you later. We're going to take a little cube in our box. Well, this one's dead too. All right.
Do you need a blue?
No, I don't. I got a purple here. Purple will do. Hey, there we go. So we're gonna take a little portion of our box. All right, it doesn't really matter what size it is. It's just a small portion of it. All right, and we're going to blow that up, and we're going to look very closely at that box. Now I lost my notes. Okay, so let's draw a cross-section of the box. All right, instead of working in 2D, then 3D is just working 2D for now. So let's just draw an axis system, right? We'll call this X, and this is Y, and then out of the board is Z. Okay, so here's our little portion of the box. Silence my phone. I'm waiting for the dealership to tell me how much money I owe them.
Too much.
Yeah, exactly. Too much. Yeah, too much. Yeah. And so inside of there we have some particles. So let's just look at one particle for now. One atom. All right, we got atoms in there. All right, and let's say it's moving along the x-axis with some velocity. So here's its velocity vector, and it's got a component along the x-axis v sub x. All right, and it's only moving in x direction. Right, so just ignore that it can't move up or move in and out. It can just move x. Recall that this box is 3D, so there's a wall on each side. And I'm going to shade this wall. Okay, so this is the side wall of the box where it's the edge of the box, if you will. And it has surface area A. Okay, so the wall of this little mini box, the surface area A. And remember what the definition of pressure in some ways inside of the system is. Pressure is a function of how much force is being exerted against the walls of our boundary by the particles colliding against them, right? So pressure is exerted by the particles hitting the wall and colliding with them. Okay, so we should ask the question, how much distance does it take for this particle somewhere to hit the wall? All right, so we can do a little bit of physics. We can say the amount of distance our particle travels in time delta t, right? Just a little bit of time, is going to be, we'll say it's delta x is equal to the velocity times the time. Right? Velocity is displacement over time, so when you multiply velocity by time, you get displacement. Okay. And so let's say, for instance, the particles hit the wall within that time. Okay? Within delta t. So within, if a particle or particles hit the wall within delta t, then the total, then all particles within the region, the volume, which is A times delta x, right? Area, again, is meters squared, and you have meters, so you get a volume. Right? So it's this surface area times the depth of the box where the particles are close enough to hit the wall. And so I'll just draw that. So like, for instance, this is the cutoff. This would be Vx delta t. All right, so if particles are on the left side within delta t, they won't hit the wall. But if they're on this side of the wall of Vx delta t, they'll hit the wall within its time. Okay. So that's A times Vx delta t. So all particles within that volume hit the wall. Okay, so that's our little, basically now this region right here, which I'll kind of briefly sketch with some dashes. This is the region of our little cube where any particle within delta t hits the wall. Okay, anywhere in that region. Anything else here isn't going to hit the wall. Okay, so now we have to ask, well, how many particles are in that region? Right, so let's hold on to this for a second. This is our volume element. So now the next question is, how many particles are in that region? Well, the way we should measure the number of particles is by the density. So the density of particles within our volume, which is within volume A Vx delta t, is what we call rho, right? Rho is density, or P. It's going to be the number of particles in that volume. So the number of particles, and let's convert it into moles. We multiply by Avogadro's number and divide by the volume. Okay. Divide by the volume of this area. So that means that the total number of particles is equal to, we'll call that N so N within this volume, in little volume, is equal to the moles of the particles in the box. Sorry, this is actually the whole box within the box. So now we got to think about the particles within the little small region. Ends up being, again, the density of the particles times the volume of the small region, which is this, A Vx delta t. All right, so let me walk through that one more time because I kind of got confused. Right, so we can measure the density of particles, how many particles there are per unit volume, by measuring the volume of the box and measuring the number of particles, or the number of moles of molecules we have in the box, right? And you divide the two, right? So we have moles per volume, if you will, or number per volume. Sorry, this is number per volume, right? Because this is moles times Avogadro's number, that gives you particles, so it's particles per volume. Okay, so that's our average density of particles in our whole box. And that means that the total number of particles inside the little box is the density times the volume that we're looking at, which is that little region right here, AVX delta t. Are we good so far on this? Okay. We'll see how this all works out really quickly here. This will all kind of break down really fast. We're going to do a bunch of physics, and then it'll all simplify. So now what we have to do is figure out how many of the particles in this region actually hit the wall. Because the important thing to note is that the particles move randomly. Right? Because the particles move randomly, that means on average, half the particles in this red region are moving towards the wall, and half are moving away from the wall. Maybe it would be more helpful to write this as Vx squared, right? Because they can go backwards or forwards. Right, so what that means is that the number of particles that collide with the wall, so I'll just kind of mark these one at a time to keep it organized. Is 1/2 n little, because half are moving the opposite way because of randomness. Half the particles have velocity Vx, and the other have minus Vx. Right? So half are moving away from the wall, half are towards. Okay, so that really means that the number that are colliding is 1/2 times the number of particles divided by the volume of the box times the volume of our small box, which is 1/2 density A Vx delta T. Okay. Now, all right, so now we've determined roughly how many particles are colliding with the wall at a given time delta t. And now we need to apply Newton's laws, because when at the point of collision, there's going to be a momentum change, right? Because the particles have momentum towards the wall, and then when they collide, they do so elastically, which means by Newton's third law that if they hit the wall from this direction and they bounce off, they're going to go in the equal and opposite direction. So upon collision, by Newton's third law, the initial momentum of the particles is the mass of the particle times its velocity. And then the momentum after collision, it's minus that. Right? So if they have momentum in this direction, they bounce, they're going to go, the momentum's going to be in the opposite direction afterwards. Okay, so that means that the change in momentum, the total change in momentum, is the difference between these two, which is mvx minus mvx. Which is 2 mvx. Okay, so upon collision, the total momentum change is double the original momentum because of the collision. We're really close to pressure. We'll come back to this part in a second. You'll see how this momentum thing ties in just a second. It kind of seems strange because we haven't really talked about momentum, but momentum has everything to do with pressure because it's about a force being exerted on a wall, as we'll see. All right, so now we can combine. So now we know how much momentum changes per particle upon collision, and we know how many particles we have. So we can calculate the total momentum change of all the particles. So the total momentum change upon collision is the momentum change for 1 times the number of particles. Well, we have both of those values right here on the board. Right? So that is equal to 2 mvx times the number of particles that are colliding, which is 1/2 NA, Avogadro's number, times the total volume of the box, times A Vx delta T. Okay, and I'm just gonna multiply all this out and simplify it. And this ends up being the moles of the particles times the molar mass, because mass times Avogadro's number is molar mass. A Vx squared delta T all over V. And I'll write that this is the molar mass. And that this is the moles. Okay. All right, so that's the total momentum change. Now we get to use Newton's second law. All right, so we've used Newton's first law, we've used Newton's third law, now it's time to use the second law. Newton's second law says that momentum let me change that again. So the time derivative of momentum, the change in momentum with respect to time, the derivative of momentum with respect to time, how much momentum changes in a given value of time, is equal to the force, or m times the second derivative of the displacement with respect to position, or the acceleration. Right, that's Newton's second law, F equals ma. Right, so the change in momentum is mass times acceleration. And pressure is force over area. Right? So that means then that the pressure that's being exerted against our wall is the time derivative, the change in momentum with respect to time, times 1 over the area. Okay? Because this is the force, and it's force over area. Okay? But we already know the time derivative, or how much momentum changes in our unit of time that we've measured, because we calculated it right here, right? Where everything's being measured in terms of delta t, right? This is our little time interval. This is how much the momentum changes in that time interval. And so that's the derivative of momentum. Okay, so this is equal to d momentum dt. So when you put all of this crap together, what you end up getting is that the total pressure against the wall is the moles times the molar mass of the particle times the velocity squared of the particle all over the volume. All right, so where can I delete this? So we don't need this. Okay, so now let me rearrange this a little bit. This says that P times V is equal to N times M times Vx squared. Okay, it's already kind of looking like Pivner, right? Now, the fact of the matter is that we've only considered motion in one direction, only in the x direction. But in fact, this is a three-dimensional system, and so there is random motion in all three directions. Right? So the particles can be moving towards walls in the z direction, which is out of the board. Could be hitting the walls in the ceiling or the floor, or either the walls along the x-axis. So these particles are moving randomly in three different directions. We've only considered one. But the thing is that they're all separate. We can separate velocity. Remember, velocity is a vector. So it's got an x component, it's got a y component, and a z component. Right? And they're all separate. They don't talk to each other. So if a particle moves in the x direction, it doesn't affect it in the y direction or the z direction. The particle, in fact, can move in all three directions independently. Okay? So, which is a really nice thing, because what we're doing is we're solving it for the problem for one direction, and all we have to do is do it the same thing twice over, right, for the z and the y direction, and then just add them all together. Okay, so because the motion is random in three directions, the average value of Vx, right? I write average, this is average. When I use these little curly brackets or these little angular brackets, that means average is equal to the average in the y direction. Maybe I should square this. Square is equal to the average velocity in the z direction as well. So that means on average the particle is moving at Vx in the x direction, and it's moving at the same velocity in the y direction and moving in the z direction as well. So that means then that Vx squared is 1/3 V total squared. Right? Because it's moving, on average it's moving in all three directions at the same speed. So that means its x component has to be 1/3 of the total velocity, right? Because they all add together. So that means that we can immediately go from one dimension to three dimensions just by accounting for the fact that they're just 1/3 of each other. So that means, therefore, that pressure times volume is 1/3 times the number of moles times the molar mass of the object times the average velocity squared. We're already getting to an interesting point, right? We have some things to deal with, right? Because what we want to derive is PV equals nRT. But notice there's no T here yet. There's no R either. R is just a constant. But notice that we have the same form, right? We have N, we have PV here, we have N. So that must mean that 1/3 mv squared must be RT. Right? But we haven't quite derived that yet. Okay, but we have an average here, a velocity, and maybe we can interpret that. Questions so far? Okay, we're halfway there. Or a little more halfway there. This is where Boltzmann distribution comes in. Right? Because we're taking averages of velocity, right? Everything's random, so we need to pull velocities out of a hat, right? And then take an average of them, because everything's random. But we have that right here, right? The number of particles with a given or kinetic energy or velocity v is proportional to e to that energy divided by kt. Right? So what we can say is that the total kinetic energy of the particle is 1/2 mv squared. So the average kinetic energy, rather, let me write that. 1/2 mv squared, which I'll just break it down as 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. All right, and so we have a formula for the energy right here. Right? This is the energy of the particle on average. Right? So we can plug it straight into Boltzmann's distribution. Right, which says that the number of particles of a given velocity, which we'll write in some v, is proportional to e to the minus mv squared over 2 kBt. Right, where the 1/2 has been distributed out into the denominator. Right, so this tells us exactly proportionally what the average, what the probability of finding a particle at that velocity is. So that means we can probably calculate an average because since we know the probability of a certain value happening, we can calculate the average value. Right? And that's what we're going to tackle. Now the problem is that this is proportional, not equal, right? And in order to calculate an average, we need to know a precise formula for the probability. But this is not precise because it's proportional to. Right, so what we can say then is that NV is equal to some constant K, which we haven't determined yet, times e to the minus v squared over 2 kBt. Problem is we don't know how to determine K. Okay, but we can figure it out pretty quickly. Let me plot this okay, at a given temperature. Bless you. So let's plot n sub v, right, which is the fraction of molecules at a given velocity, versus the velocity. And what we're going to find is it looks kind of like this. Like that, roughly. Right, and so at a given velocity, v sub I, this is the probability of finding a particle with velocity v sub I. Bless you. So now let me ask you a different question. So we know what the probability of finding a single particle at a given velocity is, right? So that probability is just this function, right? We just plug into velocity and we get a number out. Now here's a question. What's the probability of finding a particle with any velocity? So you go to Vegas, someone says pick a particle out of the box. And if it has any velocity, you win. What's the chance of you winning? 100%. So the probability of finding any particle with any velocity is 1. Right? Probability is between 0 and 1, right? Or 0% and 100% chance, right? So what that means is that if we sum over all of the probabilities of every particle, right, that we should get 1, right? So the idea is that if we sum over all velocities, our formula, n sub v, we should get 1. Because there's a non-zero probability of finding a particle at any velocity. But if it's all velocities, it should be 1. Okay, this gives us a hint on how to solve for k. Now, this is as if there are a discrete number of velocities, right, when I sum over them, right? There's velocity 1, velocity 2, velocity 3, we can count them. But this function is a continuous function. It's defined for any number, right? You can have a velocity that is fractional units, right, of whatever unit you're using for velocity. So what do we call a sum that is continuous? What math concept is a continuous sum over a function?
A limit?
Yeah, so that's an interesting idea. So let's take a limit of this as the change in delta V goes to 0, right? Delta V. Does anyone know what this is, the definition of? This is the integral from 0 to infinity of the probability times differential velocity. So what that means is that the integral, we know this to be 1. All right, so we know that the integral of this equation across 0 to infinity, right, the probability of finding a particle at any velocity, has to be 1. So we're just about to get a formula. Right, so now what that says is that 1 is equal to the integral from 0 to infinity of this k times e to the minus mv squared over 2kt dv. Right, that's our formula. Now it's kind of not clear how we do the v's because this is a three-dimensional. So we have to change this to the velocities. This is velocity, excuse me. Let me make sure I'm clear about that. Okay. Remember that the definition of velocity is this, or kinetic energy is this. So we have three dimensions. Right, so this actually changes to a triple integral, all being evaluated from 0 to infinity, along each of the three directions. So that would be k e to the minus m vx squared plus vy squared plus vz squared all over 2kt dvx dvy dvz. Scary. But this isn't that hard of an equation to calculate because we can separate it, right? This is a nasty triple integral, but in fact it's just a product of three single integrals. And I can show that to you because we can rewrite this as 0 to infinity. Let me bring the k out so we don't have to worry about it right now. E to the minus mvx squared over 2kt dvx times the integral from 0 to infinity for the y component dvy times the integral from 0 to infinity of e to the minus mvz squared over 2kvt dvz. Right, so it's really just three one-dimensional integrals, right? We can separate the whole thing, right? Because remember that e to the minus x plus e to the x plus y is e to the x times e to the y, right? So we can separate all the components out and just multiply them together. Right? And this is all equal to 1. I'm not going to do this integral. Actually, it's really, you can look up this integral, e to the minus x squared, or e to the minus ax squared, where a is m over 2kt. It's actually a well-known integral, and you can just, you can look it up we're not going to have to do it. It's not a big deal. But anyway, you can integrate this out, and what you find, right, you solve for k, right? That's the thing we want to solve for, right? Because this is going to give us a number, this is going to give us a number, this is going to give us a number. We have an unknown and a known, so we just need to solve for k. The k is the mass of the particle divided by 2 pi kBt to the 3/2 power. So now we have a formula. We can now calculate the number of particles at a given velocity by just plugging in this number, m over 2 pi kBt to the 3/2 e to the minus mv squared over 2 kBt. Like so. This describes everything we know about the energy, or the state of the system, given a temperature and given a mass. Right? That's all it depends on. And if the mass imagine that the mass gets bigger, then this number gets larger, right? So the particle slows down, right? Heavy particles move more slowly than lighter particles at a given temperature. If we increase the temperature, everything moves faster because this number gets smaller, right? So does this number. This gets smaller faster. This gets bigger faster than this gets smaller. So this is, anyway, it's not a big deal. But the idea is it makes sense perfectly, right? And for instance, here's a good example of it. This is something, my wife works at a Five Below store. I don't know if you've ever been to Five Below, but she's a manager there. And they have one of those they got helium for balloons. And one of our coworkers asked me, because my wife is a nerd like I am, and she told them about how helium is getting increasingly rare. And they asked me, said, why is helium so rare? Why can't we get more? And the problem with helium is, unlike other gases, is that helium is so light that its average velocity is faster than the escape velocity of a particle on Earth, right? It moves faster than the gravitational trap of the Earth itself. So any helium in the air escapes into space. So we can't keep it, unlike CO2 or oxygen or nitrogen, which are much more heavier. They move more slowly on average. They don't have enough momentum to escape the Earth. So and this explains it perfectly, right? If you have a very small mass, then you have a very large. At high velocities, you have a large probability. So on average, light particles move faster than heavy particles at a given temperature. Okay. Well, this is great. This literally is the probability distribution of particles moving, right? Given any velocity, we can calculate the probability. So that means we should be able to find the average of this, right? So for instance, if this looked like a bell curve, which it kind of does, so this is what NV looks like a bell curve at a given temperature, and mass. And the question we're going to ask is, well, what's the average velocity? Right, the middle of the bell curve is the average velocity, the mean velocity. Right? So what is the mean velocity of our gas? We'd be more careful, it's v squared. Right? If we do v, then we have to worry about the sign. So what's the average, the square velocity of our gas? Right? That's what we need to know because we can just plug it in right here. Right? That's ultimately what we need to calculate. Now we have the statistics to actually do that. Okay, so now we just have to take this function and calculate the average velocity of this distribution of velocities. And then plug it in. You already know what the answer is going to be because you know this is going to be nRT on this side, and that's exactly what we get. So let me show you that. Maybe you saw this formula once in calculus and then never used it again. But the average value of an observable, x, for instance, just anything, could be velocity, could be position, is equal to the integral across all space, which is for here 0 to infinity, of the variable times the probability function, which is this. So that would be times, we'll just call it like p of x dx, right? This is p of x, our probability distribution, right, or bell curve for velocities. Right, so what we want to do now is calculate v squared. So that's going to be the integral from 0 to infinity of v squared times our formula for the probability. Like that. Right, so we're going to take this formula, multiply it by v squared, and integrate. And that'll give us our mean. Okay, so I won't go through the math, right? We're going to do the same thing again. We're going to have a three-dimensional integral where we have v squared can be expanded into vx squared plus vy squared plus vz squared. Right, I'll just write it out just to show you. Times m over 2 pi kBt. So the 3 halves, e to the minus m vx squared plus vy squared plus vz squared. Again, I'll never make you have to do any integrals like this. But it's important to look at it just to get a sense. Like that. Right? So we have our average quantity we want to measure, v squared, and we have our probability distribution function. Right? Probability of finding a velocity at a given temperature and mass. Right? And this will give us the average velocity. So anyway, you can run this calculation, right? And you end up getting a really, really simple equation. This ends up simplifying to 3 kBt over m. Right? All this crazy math It's one of these things. E to the minus x squared is a beautiful integral. It always simplifies very simply. It's always a great simplification. Even when you multiply it by something that's squared like this, you always get really beautiful results from it. It's a really lovely integral. So we have this really complicated equation. Do all the algebra. You have to do this in polar coordinates. It's a miserable affair, but it simplifies beautifully into a very simple equation. We're in. Notice there's a factor of 3 in here because it's 3 dimensions times a factor of 1/3. Right, it goes away. Right, it all cancels out beautifully. Right, so when we plug this in, we get PV equals 1/3 times n times m times 3 kT over m. We have a discrepancy in the units here because this is molar mass and this is mass. So we have a factor of Avogadro's number to deal with. And a way that we can fix this really easily is to multiply Kb by R. So n times m, 3 kBt times Avogadro's number, divided by Avogadro's number, multiply both sides by Avogadro's number, and this ends up being, everything cancels out nicely, and you get nRT. Call that again that R is the Boltzmann's constant times Avogadro's number. Right? There's our ideal gas law, right? So this is really beautiful. We've taken the very simplest assumptions in Newton's laws, right? That we have floating particles that don't interact with each other. They move around randomly in 3 dimensions. And we came up with this really, really beautiful, what they call an ansatz, or like an assumption, that these particles move randomly, and so therefore the probability of finding a particle at a given energy is this value right here, this exponential. And this exponential simplifies everything, right? This is the key to it all, right? Because we get these integrals of e to the minus v squared, and integrals of e to the minus v squared simplify dramatically, as they do here, right? And so by making these small assumptions in Newton's laws, we can average out all of the random effects, and it turns out the math works out perfectly, and you get this lovely equation. PV equals nRT, the ideal gas law. Well, what does this tell us? Well, this tells us that an ideal gas, again, I mean, let's do the unit analysis for a second. What are the units of RT? Well, first, let's just break it down one by one. What are the units of temperature? Kelvin. What are the units of the gas constant? Joules per mole per Kelvin. And this is moles. So when we multiply all these together, we get joules, right? Because the Kelvin and a mole cancel out. And if you've done the homework problem, the last homework problem on the exam, what units are PV in? Joules. This is just conservation of energy. Right? What we're going to learn is that you have this thermal energy, which arrives from kinetic motion, right? Random kinetic energy motion of our particles. Right? You get this nice nRT. And that it's equal to what we call the work, the pressure work. And we'll see a little bit more of that next week. We'll talk about pressure work. Right? This is the work, the effort being done by the particles colliding against the wall. Right? That's the kind of work we're doing. Right? Where the molecules are pushing against the wall. The amount of energy they exert by doing that in a given volume is P times V. And that's equal to the total thermal energy that's available to the system. Right? That's all PIV-NERD is. It's literally just saying that energy of work is equal to the energy of the heat. Nothing more. But it's thankfully because of this beautiful math, right, with this Boltzmann distribution and these integrals, that you get this really lovely simple equation. All right, so we've come up with our state, right? We can now express the pressure of this system as nRT over V. Right, so given any volume, any temperature, any number of moles, we can always calculate the pressure of our system. We now know how to calculate any property of our system because we have a formula that tells us where you plug in a bunch of variables and you get one out. Right, so now we've described our box of gas ideally, and now we can start doing math and work on it. We can start asking questions, right? What happens to this box of gas as we start to compress it, right? What happens to this box of gas as we increase the temperature? How much energy does it take to increase the temperature of the box? Right? That's an interesting question. Right? And we're going to tackle all of these problems in this class, right? Because we'll be able to we can now express every property of this box precisely up to the approximation of the ideal gas law, given any condition that we're in, right? Any questions about that? Now I know that was a little dull, but I think it's important because it ties in together all of the rules that we've learned from physics, intro physics, and the idea of randomness. And by doing things randomly, right, by assuming that the system is random, we can simplify our math considerably. Right? And this is the approximation that we make in this class a lot. This is the whole point of thermodynamics, is that it is impossible to take a system, a chemical system, or any material. It's not impossible, but it's completely impractical, and analyze it on an atomic level, an atomistic level, right? Talk about the volume, the temperature, the energy of each particle independently of each other. Right? That's a very difficult task. You can do it for a small number of particles, as we'll learn eventually, but for a very large, when you're on an order of a mole, it's impossible. And especially since they're all moving randomly, right? It's even worse, so we'll come to learn, is that these particles are indistinguishable from each other, right? It is physically impossible to label atoms, 1, 2, 3, 4, 5, and pull one out and say this is atom 1, this is atom 2, atom 3. They're all indistinguishable. You can't tell any of them apart. They're all exactly the same, right? Every copper atom, every helium atom is exactly the same from each other. You can't tell them apart. The only thing you can tell is how many you have, but you can't separate them independently, right? So we can't really do anything at a very fundamental level in this system. But if we assume that the system is moving randomly, and that we're up to chance, right? And that the system goes through many, many configurations at a very fast rate, right? If there's 10 to the 20 particles in here, there's tons of them colliding at different velocities, right? Your sample size is massive, right? So we know that the idea of a mean, of an average, is a good quantity here because the amount of their sample size of events, of collision events that define pressure, is massive, right? So we know that the average is a good number to value, or a good number to measure. It's an accurate measurement of the statistics. And so by making that assumption that the system is random and that we can't actually distinguish individual particles in the bulk, by just giving that up a little bit, we can simplify our math considerably and actually come up with a model that works really well. That is something we'll come and see time and time again in this class. For instance, I'll give you a hint, or an interesting part. We'll do this problem on the homework in a couple weeks. I think it'll be on the third problem set. I'm going to give you a hint, a description, just in kind of the last 5 minutes of class, about how random things are and how good the approximation that systems move randomly is. Let's imagine that you have a box. Okay, we're always going to see the box. And let's put a wall in between two sides, A and B, all right, that we can remove. All right, so when the wall's in, nothing can exchange between them. All right, and we're going to fill this box, both sides. So basically we're going to take the wall and take the wall out and fill the box with 1 mole of atoms. Okay? So when we put the box in, on average, there's going to be 1/2 mole here and 1/2 mole here. Okay? So the number of particles in A is roughly 3 times 10 to the 23. Right? Because a mole is, this is the unfortunate labeling because it looks like Avogadro's number. The number of particles in A is 3 times 10 to the 23, right? Half of a mole. And in B is 3 times 10 to the 23. Okay. So now I'm going to take the wall out. Okay? Right? And if we pretend to subdivide the wall, subdivide the system, you still have half a mole on one side and half a mole on the other side on average. So now the question I want to ask is, imagine it takes 1 nanosecond for a particle in A to cross over to B, to side B. Okay. So the particles exchange from A to B every nanosecond. How long, right, and they're moving randomly, how long do we have to wait until we observe N sub A being 1/2 mole, right, 1/2 Avogadro's number, minus 10 to the 10, and B having an extra 10 to the 10 particles. Okay, so how long do we have to wait at 300 Kelvin, right? So let's just say this is at 300 Kelvin. How long do we have to wait until just miraculously there are 10 to the 10 extra particles on B over A, right? That there's an extra amount on B, right? This seems like a lot, but it's not, right? So 10 to the 10 over 10 to the 23, so it's minus 10 to the 13 mole, right? Which is 100 picomoles, or 100 femtomoles, right? So how long do we have to wait until there's an extra 100 femtomoles on the right side than the left side, right? Not very much different. It's a tiny fraction. You can do this calculation, and we'll walk through it on the third problem set because I love this question. The answer is that the time that you have to wait to observe this, right, this is a tiny discrepancy, right? 10 to the minus 13. Time you have to wait is on the order of 10 to the 60 seconds. It's multiple times the length of the universe, the age of the universe. So this is amazing because what our assumption is that on average, half a mole is on each side, right? But even if we get to a discrepancy of 10 to the minus 13 off of that assumption, very tiny, tiny amount, we have to wait longer than time has existed in this universe. Right? And this is why the idea of randomness in thermodynamics, the idea of thermal equilibrium is so powerful. Because when you get to the scale that we care about in chemistry, right, at a molar scale, there are so many possible arrangements of the system. There are so much, as we'll learn, so much entropy, so much disorder, so many options for the system to arrange itself in, that in order to see a tiny minuscule deviation from our equilibrium assumption of half and half, we have to wait an insane amount of time. Right? It's basically physically impossible. Right? This is why it's good. Right? So that's why thermodynamics works, why the randomness works. Next semester, we're going to get to a position where we're going to talk about one atom at a time. Things are going to look a little weird. But once we get to very large amounts of system, the bulk limit, if we will, the bulk limit, a molar scale, discrepancies from randomness are tiny, absolutely tiny, imperceptibly small. So that's why this works so well, right? This is why, even though we make all these crazy assumptions, I said that this class was about taking things at first principles without assumptions. We've made some pretty strong assumptions. Yeah, but these are really good assumptions because tiny discrepancies from those assumptions lead to absurd conclusions. Right? So we just ignore them. We just ignore these things. They just don't matter because There's literally nothing you do or scientists study where they care about things that are on the scale of 10 to the 60. I mean, even cosmologists don't care that much about things that last this long. So that's why thermodynamics is a really nice approximation of things. Right? We haven't really lost much by making these assumptions about randomness, because if we assume otherwise, we lead to absurdities. Absurdities that are not physically meaningful. Any questions? Okay, so that's all I have today. Actually, I got through this pretty quickly. Last year it took 2 lectures to get through this. So we're not going to really dig deep into this math, right? We've learned this a formula, and this is a really powerful formula. And if you remember from when I talked about these assumptions, that the idea is we're going to solve an easy problem, and then when we get to the things that break this, right, we're talking about molecules having attractions to each other, which they do. We're going to make small corrections to this, right? And we're going to come up with a new formula that's a correction to Pidner. And the corrections are small. So that's what we're going to do on Monday, or Tuesday, sorry. We'll come back to this. We'll talk about real gases and how they're different from ideal gases. Talk about how we represent them mathematically, and do some calculations. So have a lovely weekend. Homework's due tomorrow night at midnight. If you have any last-minute questions, I think there's a 6 to 8?
Yeah.
6 to 8 tonight in CLR if you have questions, or you can email me tomorrow. I won't be able to answer anything tonight, but tomorrow I can answer emails. Yes, sir.
Oh, well, you didn't answer
Yes.
in our professional.